This is a video presentation for Electronics Engineering Laboratory VEJ 20701, and this is Experiment 1. Our lecturer is Sheikh Mazita binti Muhammad. As for our team members, we are led by Wong Bo Suan AE 190084, and our first member is Fu Chun Fai AE 190101, and me myself, Chan Jensen AE 190080. Next, we'll proceed with the video simulation of the experiment.
Hi, Checkmaster. My name is Wong Bozon, and I'm gonna present about the characteristics of the silicon and germanium diode circuit. So, we are using this multi-sim as our main simulation software. This is a circuit for the silicon diode. So, the silicon diode is the 1N4001 model as given in the lab sheet, and for the germanium diode, it's the 1N34. And the two circuit is actually the same, just the difference in the materials of diode. So, in order for us to get the readings of the VR and the VD as well, we will run the interactive simulation, and we could obtain the value by double-clicking the multimeter. And we could change the parameters which we want by clicking it here. Same as for the VD, and it's same for the germanium diode. We'll start the interactive simulation, and it's same. We could read the voltage which at the resistor and the diode as well. So in order for us to obtain the table for the different inputs, we could open the table by choosing DC switch, choose from 0 to 5, and select the outputs that we desire and run. We could simply obtain the curve which the voltage at the diode where we are using different power inputs. So in order to see the difference between the silicon and germanium diode, I will overlay the two graphs, and we could see that the green color line is for the germanium diode and the red color line is for the silicon diode. So the shape which was presented by the two graphs was actually similar. Just you can see that they have a very obvious voltage drop at different point, which the silicon diode is around 1, but the germanium diode is around 0.5. This is because the diode has a depletion layer, and it requires a minimum voltage, which was also known as threshold voltage, to pass through it in order to let the diode connect the entire circuit. So we could estimate from this graph approximately the threshold voltage of the silicon and germanium diode. So for the silicon diode, it's almost around 700 millivolt. So it's similar with the theory. Since the theory, the threshold voltage for a silicon diode is around approximately to 0.007 volt, and for the germanium diode, it's approximately to 0.3 volts. And here, we could see that the results obtained when it's stable, the curve is stable, it's approximately 0.3 volt. So that's all from me. Thank you, Checkmaster.
Hi, Sim Isa. My name is Fu Junfei. Now I'm going to present about the characteristic of general diodes. This is the general diode circuit with the real bias, and the diode we use is the 1M5231B. In the circuit, we have two multimeter. This multimeter is to measure the reverse current in the diode circuit, and this multimeter is to measure the voltage across the diodes. To measure the current and the voltage, we have to run the simulation. Simulation, and when press on it, we can see the ampere across the diode circuit and the voltage across the diode. Next, to obtain the graph IZ versus VD is a reverse current versus the voltage across the diode. We have to go to the DC swap and the output. This is the graph of current versus voltage. From the graph, we can see that the general voltage is approximately 5 volts when the voltage supply getting greater than the general diodes. The amount of the current flow through the circuits increase when the voltage getting higher. Next, we are going to see the diode application for the triple circuit. This is the triple circuit that we have created. In this circuit, we have two oscilloscopes. One oscilloscope is to collect the input waveform, and one oscilloscope is to collect the output waveforms, which is connected to the diodes. This is the input waveform generated by the function generator. This is the output waveform after the power is passed through the circuit. From this graph, we can see that the positive part remain and the negative part is gone. This is because when the positive cycle, the diode was become open circuit, so the input voltage is equal to output voltage. When during the negative cycle, the diode becomes short circuit and allow current to flow through, so the output is present. So that's all for me. Thank you.
Next, over here we have the bias negative clamper circuit, where in this case we have an input of 10 volts peak to peak, but for this we use a 5 volt peak, which is 5 volts for both positive cycle and negative cycle. And here we have our capacitor at 10 microfarads and our resistor 10 kilo ohms, and our diode, which is the IN4004 with an additional voltage DC, which is 3 volts over here. And then we have connected the oscilloscope for the AC input, and also to the our diode, which is the clamper for this case. And I will now run the simulation, and as we have observed over here, this is the graph for our AC input, and this is the graph for our diode. And as we can observe from both graphs, the positive cycle, or the peak, or the voltage positive peak is obviously lower than the negative peak. Well, this is because during the positive cycle, the diode will be connected and conduct the entire circuit, but the output voltage will be equivalent to the reference voltage. And during the negative cycle, the diode was placed in a reverse bias order, and it will act as an open circuit, so the output of the voltage will be across the capacitor, and this explains why the voltage for the positive cycle and the negative cycle has a difference. So this is the lab simulation for our circuit, and that's all from us. Thank you.